Complex ions. So we learned about Lewis acids and bases. Remember, that has to do with donating or accepting electron pairs. So a Lewis acid is a good electron acceptor. Water molecules can act as Lewis bases because you've got lone pairs on the oxygen, electron donors. And so they can hydrate transition metal ions. So here's an example. Silver ions in solution actually are not just floating around by themselves. They pick up a couple of hitchhikers. And so we've got water molecules making these coordinate covalent bonds with the silver. So silver plus doesn't actually exist as a bare ion. So this is called a complex ion because it's complicated, right? You've got a central metal ion, and then you've got one or more things attached to it, and those things are called ligands. So a ligand can be a neutral molecule, or it can be an ion that acts as a Lewis base, with the central metal ion acting as the Lewis acid. If a stronger Lewis base comes along, it will displace the first one. So here we have silver with two water ligands, and if we add ammonia to that, ammonia is a stronger Lewis base than water is. And so it will take the place of water on that silver ion. A lot of things are actually hydrated, actually form these complex ions in solution, and we generally just ignore it, right? So for simplicity, we'll often write it like this. Ag plus 2NH3 makes this complex ion. So in a way, it's like what happens with the the ionization of water. And we're actually, what we have is we have two water molecules, and one gives a hydrogen ion to the other, and then we end up with hydronium and hydroxide. But we often kind of abbreviate this and leave out that water molecule that's holding on to the hydrogen. So it's a little bit like that. So equilibria, there's an equilibrium constant expression based on this equation. Again, products over reactants raised to the power of any coefficients. And this constant is called the formation constant because this reaction here is showing the formation of a complex ion. So formation constants are another thing that can be looked up. This is from chapter 18 in your book. I think there's another more extensive table in one of the appendices. Here we've got a whole bunch of different kinds of complex ions. So how do we identify a complex ion? Why are these not considered just polyatomic anions? Well, these are all going to have metals in them, right? So these have metals in them, and most all of the polyatomic anions do not have metals in them. Chromate is funky. So we have, this looks like a chemical formula, right? AgCN2. Except there's an overall charge. It's an ion. That green salt that we made was a complex ion. Potassium was the counter ion, and what we were looking at and trying to figure out was the iron and the oxalate. And so we were looking at this iron oxalate complex ion and trying to figure out, well, how many oxalates are there for the iron? And I know you guys are still working on that one. So you'll notice that these formation constants are quite large. Some of them are super, super large, like this one, 10 to the 43, right? That one, for all practical purposes, that goes to completion, right? There's almost nothing left. Okay, so we can do equilibrium problems with complex ions. You mix a 125 ml sample of a solution that is 0.0117 molar in nickel chloride with a 175 ml sample of a solution that is 0.25 molar in ammonia. After the solution reaches equilibrium, what concentration of nickel ion remains? And they're giving us the formation constant. Oh, that was the answer. Go away. For this complex ion, you are not expected to know, just from the first part of that, what complex ion it's going to form. Sometimes you can get more than one complex ion, so that's not something you need to worry about. But so here's the complex ion. So the first thing we want to do is write an equation, a chemical equation, for the formation of that complex ion. So we've got nickel ions, and we've got ammonia molecules, and those are going to be in equilibrium with the complex ion. And then we need to balance this equation. So our complex ion here has 6 ammonia molecules, and so we need a 6 here. Okay? We'll make an ice table. Those are never going to go away. I see. So we need to find out the initial, actually, hold on. We're not doing that just yet. The first thing that's going to happen, because this is a very large number, right? That means the products are highly favored. So we're going to do like we did in the titration calculations, where we're adding sodium hydroxide. We're going to have that react with everything all the way, and then we'll look at an equilibrium shifting back. So we'll start with looking at the amounts added in moles or millimoles. So we have 125 milliliters of 0.0117. So 125 times 0.0117. So we've got 1.4625 millimoles of nickel. And we have 175 milliliters, that's 0.250 molar in ammonia, and so that's 43.75 millimoles. And none of the complex ion to start with. So we're going to look at this reacting is basically a limiting reactant problem. There's a lot more of the ammonia, but we also need 6 times as much. But 43 is way more than 6 times bigger than this. So this is going to be our limiting reactant. So that's going to, we're going to react all of our nickel, ending up with 0. And here, this is going to react 6 times the quantity of nickel, because it takes 6 of these, right? So 43 minus 6 times 1.4625. .975 millimoles. And how much of this complex ion are we going to make? 1.4625. Yes.
That's 34.9725.
So you got 9725 there?
Yeah. I think you just misread it a little bit. Is this 34?
Yeah. Actually, that makes sense.
You get the same answer.
It should be 34 because you have 6 of them, subtracting it from 43.
Oh, I thought you were talking about a 2.5 here.
Oh,
no.
It's the 9. Okay.
Yeah.
Yes. Yeah.
Yeah, 34.
It's 34. Yeah. Mhm.
I just had a hat on.
It just, yeah. There was just a stray mark there. Okay. Any questions? Yes.
Can you just explain real quick why you used the 1.465?
I used this because doing just a little mental math, I figured out that this is going to be our limiting reactant.
Oh,
Yeah, because I need 6 moles of that for every 1 mole of this, but 43 is way bigger than 6 times of this. Yeah. Okay, so now we've got millimoles. We can do an equilibrium calculation. This is what we've done is we've pushed the reaction to completion to the right. All the products could possibly be made. But I think we all recognize now that nothing actually goes completely, right? It's going to come back a tiny bit. There's going to be at least a couple nickel ions left in this solution. So then we're going to bring it back. So we need concentrations, molarities, and so we need to look at our total volume. So 125 milliliters plus 175 milliliters. Is 300, right? Did I do that right? So to turn these into molarities, we're just going to divide by the volume in milliliters. But you can't write with an eraser. Keep trying.
Technically, you could.
Yep, but not on here. Can anyone confirm those numbers? Okay, good. So now we're going to use these concentrations in an ice table and look at the equilibrium. So we've got our arrow here. So this is going to react backwards a little bit. That's going to be minus x. What's the change for this one? Plus 6x. And the change for nickel? Plus x. So then we end up with x, 0.1166 plus 6x, and 0.004875 minus x. So we can put these into the equilibrium constant expression. Bless you. So the formation constant is going to be the concentration of our complex ion divided by the concentration of the nickel ion and the concentration of ammonia to the 6th power. That's important. So we've got 0.004875 minus x, and we've got x. We've got 0.1166 plus 6x to the 6th power. Yeah.
Since, if we're going backwards, wouldn't it be the word KF? Since like.
That's a great question. So I'm talking about the equation going backwards, and wouldn't we have to invert KF, right? We would if we were writing the equation backwards. But I'm not writing the equation backwards. Writing the equation backwards, then my equilibrium constant would be nickel and ammonium over the other one. So it doesn't actually matter which way the equilibrium is shifting. It's just, are you writing the equilibrium constant expression for the reaction as written? Does that make sense? That was a great question. Well, that looks like a mess, doesn't it? What could we try to simplify that a little bit? X is small. So we'll see what happens if we do x is small. Wrong color. And that was 2.0 times 10 to the 8. So solving for x then, I'm going to get 0.004875 divided by 0.1166 raised to the 6th power divided by 2 times 10 to the 8th. And I got 9.7 times 10 to the minus 6. Which does look pretty small compared to both of these numbers. So what does x represent? X represents the nickel concentration, right? We could use it to find these out, but x is small, so adding or subtracting it isn't actually going to make any difference. But our nickel concentration is expected to be 9.7 times 10 to the minus 6 molar. Any questions? Yeah.
So when doing x is small, you can ignore x's even if they have a coefficient in front of them?
Yes, you could. X is small, we're going to ignore any x that is added or subtracted.
Okay.
If it's multiplied or divided, you have to leave it in there. But here, even though we're adding 6 times x, we can ignore it. Because 6 times that number is still less than 5%.
That's good.
Yes?
Where do we use x is small even if we're looking for that specific concentration?
Mhm.
We're not subtracting things, but
Yeah, even when we have x is small, really the only thing we're going to get is x. Because we are assuming that the change here is so small that it's not significant. And so what is a little disturbing is that if you ask, well, what's the equilibrium concentration of the ammonia, or the equilibrium concentration of this? Well, it would be the same as the initial from the ice table. Because when you subtract that teeny tiny number, it's way off beyond the significant figures. Did that answer your question? No.
Not really.
Keep asking.
So, basically, my question, I know it's like negligible to the other two, but I'm saying, wouldn't it make X slightly different? Because I'm trying to find specifically the concentration of nickel in that. So X would be slightly different.
Well, X could be slightly different. Let's find out.
I don't know if that makes sense.
So I'm going to do a number solver. Let's see what we get. 0.004875 minus X divided by X times 0.1166 plus 6. X raised to the 6th power. And that is 2 times 10 to the 8. It's thinking. I probably should have fed it our number to make it go faster. Okay, you didn't like that.
It's pretty close. 9.65. So 9.7.
So you got 9.65
Yeah.
times 10 to the minus 6.
I just didn't know if it was going to make any difference.
Yeah.
Yeah.
Right.
It's different than subtracting or adding besides those. So sure.
Well, the idea here is that subtracting X from this number is like taking a semi-truck full of peaches and removing one peach. Does the mass change? Yeah, but the scale you're weighing it on can't measure that precisely, right? So here we're taking off a teeny tiny bit. Here we're adding 6 peaches to a different truck. And so for practical purposes, these numbers don't get changed. And that's the whole idea behind X is small, which really is just to make the math easier. Because they didn't used to have, a little piece of plastic in my pocket that solves an equation like that. When I was in school, that was like a big basement full of computer to do something like that, maybe. Yeah,
My calculator's failing.
yeah. So, you feel better about that?
Yeah, a little bit.
A little bit? It's still disturbing.
Well, because I understand what X is small is for, and I get that.
Mhm.
Sorry for going on like a
No, that's
side
okay.
thing, but my whole deal was it has nothing to do with the other two, because we're trying to find a specific concentration for nickel, right? So X itself should matter.
Well, this X, where it's being multiplied or divided, matters a great deal. Because even if you have an incredibly small number, 10 to the minus 72, right? If you're multiplying or dividing by that, it makes a huge difference, right? Whereas if you're adding or subtracting, it doesn't make any difference at all. So. Well, look at that. The book got 9.6. So complex ions can affect solubility. So if your metal cation forms complex ions, then the solubility of that compound is going to be greatly increased when you're in the presence of Lewis bases that can form complexes. Most common Lewis bases that increase solubility are ammonia, cyanide, and hydroxide. So that's what this would look like. So here we have ammonia plus silver chloride. Silver chloride is generally thought to be insoluble. But we know that a little bit of it does dissolve, right? So what's happening here is that a little tiny bit of the silver is dissolving. We could, write that out up here. Come on. So if we have even one silver ion over here, right, the ammonia molecules are going to see it and form this complex ion. Well, what does that do to the free silver concentration? Takes it down. So what does this equilibrium do? It shifts to the right and makes more. And the ammonia comes and takes it down. And so it shifts some more and it takes it down over and over and over and over again, right? You get the idea.
Does that mean it dissolves very slowly?
Not necessarily, but we're not talking about speed here. We're talking about basically position of equilibrium or how much dissolves. You ever wondered why there are so many household cleaners that have ammonia in them? Ammonia complexes a lot of stuff, makes it more soluble, so you can wash it away. So we use it in spite of its stench. It smells horrible. So here are the two equations here. So silver chloride, solubility product constant, 10 minus 10, right? But the formation constant for this complex ion is 10 to the plus 7. So if we add these two chemical equations together, right, we see that the silver that is produced here gets used up down here. We add these together, we get this. When we add chemical equations, we multiply the equilibrium constants. And so now the equilibrium constant is 3 times 10 to the minus 3, significantly larger than it was for silver chloride dissolving in water. Now, is it super soluble? No, but it's a lot more soluble. Any questions?
What counts as super soluble?
Well, what counts as super soluble? Where's the line between rich people and poor people? Right? Depends on your perspective. So let's look at this one. Which compound, when added to water, is most likely to increase the solubility of copper sulfide? Sodium chloride, potassium nitrate, sodium cyanide, or magnesium bromide? So, we're just starting to talk about this, but do you recognize any of those anions as things that
C.
form complexes? It's C, the cyanide. That's not fair. Right there. Yes. Other than that, you would have to go maybe look at the solubility tables and see if there are any complex ions of copper and chloride, copper and nitrate, or copper and bromide. Probably not. Did you have a question?
Do we have to memorize those most common Lewis bases?
No, I don't think so. Amphoteric metal hydroxides. So a lot of metal hydroxides are insoluble or only very slightly soluble in pH neutral water. And that's why when we talk about strong bases, it's almost always the alkali metals, hydroxides, lithium hydroxide, sodium hydroxide. Those are soluble, but most other metal hydroxides are not very soluble. But some of these metal hydroxides are amphoteric. Remember what that means? It can be both an acid and a base, okay? And so for metal hydroxides like this, their solubility will increase in a basic solution. So this is aluminum hydroxide, not very soluble. But in a basic solution, we have hydroxide ions, which are also ones that form those complex ions. And so we can form this compound of aluminum with 4 oxides and a -1 charge. This is going to be soluble as opposed to the aluminum hydroxide. So you can get this to dissolve at high pHs in a basic solution. Oh, I skipped this one. Metal hydroxides are more soluble in acidic solutions. Why is that?
It takes the hydroxide.
Takes the hydroxide away. So even if this is not very soluble at all, right? What if one dissolves and the acid eats up the hydroxides and is just going to keep pulling it over, right? So that's how they're more soluble in acids. So let's look at this hydrated aluminum ion. So we learned back in chapter 17 that Al3 plus is one of these small, highly charged metal ions that can act as an acid. So here we can have the aluminum ion hydrated with 6 water molecules, and that can interact with a water molecule and donate one of the hydrogens and forming a hydronium ion, and then we're left with 5 waters and a hydroxide on the aluminum. If we add base to this solution, we're going to be removing this hydronium that got formed. That's going to shift this equilibrium to the right, going to remove more protons from the complex water molecules, right? And so then this guy can react with hydroxide and form this guy. Isn't that really confusing? There's so many H2Os and OHs. This Al H2O3 OH3 is equivalent to aluminum hydroxide. It's got 3 hydroxide ions, and these are just basically complex water molecules. They're like groupies, right? They're just following aluminum everywhere he goes, or like really stuck on him. So if we're adding base, and as we change this complex ion, we get to this guy, which is not soluble. But if we add more base, then we pull off more of these, and now it becomes soluble again. So aluminum is very weird because it is insoluble at low pHs. It's insoluble at neutral pHs, but it's soluble both at low and high pHs. Very strange. Here it is trying to explain this in pictures. So here's what aluminum would look like in an acidic solution. We've got the aluminum ion here, and we've got 6 water molecules hanging around. pH neutral, we're going to end up with aluminum hydroxide. I'm not sure really how we're supposed to make sense of what that looks like. That looks like a mess. Anyway, over here in a basic solution, now see what's happening here, this one compared to over here. Here, these are all water molecules, and here, some of these have lost their hydrogens, right? And so that makes this into an ion again, and it's going to be soluble. pH-dependent solubility of aluminum. Other things do this. So aluminum, chromium 3, zinc, lead 2, tin 2. You should remember that aluminum does that. I don't think you'll ever need to remember that the other things do it, but other things do that. The extent to which a metal hydroxide will dissolve in both acid and base depends on the degree to which it is amphoteric. Some of them are more amphoteric than others, and so then they'll be more soluble.